Do 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 do. Oh. Do 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 do. As around the sun, the earth knows she's revolving, and the rosebuds know to bloom in early May. Just as hate knows love's a cure, you can rest your mind assured that I'll be loving you always. As you can't reveal the mystery of tomorrow, but in passing we'll grow older every day.
Good morning. Colleagues, please take a seat. Yes, seems almost time. Can we start? Some colleagues are coming, and I see. Colleagues, please take a seat. Thank you. All right. Good morning, everyone. Welcome to the 15th International ISAC Congress. My name is Durwood Khan Suragan. I am one of the local organizers. For this official opening, we have two wonderful speakers. So let's begin. Our first speaker is Vice Provost of Nazarbayev University, Loretta O'Donnell. Please.
Good morning, good morning, good morning, and welcome to everyone who's here today. On behalf of Nazarbayev University, it gives me great pleasure to say a few welcome words to you. Distinguished professors, students, colleagues, and so many honoured guests, as well as visitors. We have some top-notch researchers who are here today, visiting us from China, from Switzerland, from Kazakhstan, from the Russian Federation, from Azerbaijan, from Italy, from Australia, from France, from all over the world. Wherever you come from, you are very, very welcome here at Nazarbayev University in the heart of Central Asia. This is a historic conference, and it's historic for several reasons. It's the first time that a conference of this size, of this scale, of this scope, and of this distinguished scholarship is being hosted here in Central Asia. We are truly honoured by your presence, and we are so delighted that you're able to join us in person here today. Around 500 people are expected to join the conference over the next few days from 50 different countries. We have very distinguished scholars. We also have students. Can I just have a show of hands? Who in the audience is a student? Undergraduate students, put your hands up. You are very welcome. Master's students, please put your hands up. Okay, we've got a few as well. And doctoral students. I know there's several from Russian Federation. You're very, very welcome. As we all know, mathematics is a universal language. It's precise, it's elegant, and it's profoundly powerful. Mathematics transcends borders and cultures, as we can see here today. And the scholarship of mathematics thrives on open dialogue and bold ideas. So this conference is a symbol of that coming together. And in doing so, as the host for this conference, we affirm Central Asia's role as a hub for intellectual exchange and academic excellence. Even though for many of you it might be your first visit to Kazakhstan and to Central Asia, in a way you're visiting your intellectual home, because we're gathering on a land that's long contributed to the scholarship of mathematics, from the courts of Samarkand, Bukhara, and other places in the region. Central Asia has been a thriving centre for mathematical innovation. Thinkers like Al-Khwarizmi, who did a lot of work in Baghdad during the Golden Age, whose name gave us the word algorithm, and of course Al-Farabi, who helped preserve and expand Greek mathematical knowledge, was also from this region. So given our legacy, we renew our responsibility during this conference to nurture the next generation of mathematical minds. So the year 2025 is meaningful. It's the 15th anniversary of this very prestigious ISAC conference. And it's also the 15th anniversary of the founding of our university. And can I say thank you to two of the founding members, Aseli Valieva, Kadisha Dareva. If you could please stand up and just say hello to the audience. These are two members of our university, members of Managing Council, who were here in the very, very early and challenging years of this university. They've seen us through to this point. In just a decade and a half, we have emerged as the leading research university in Central Asia. And it's not just us saying that. That's been the ranking system, Times Higher Education World University Rankings. It does demonstrate that we're committed to global engagement and academic excellence on the world stage. For the undergraduate, master's and PhD students here today, I want you to know that part of our commitment to scholarship is for our professors, as appropriate, to publish with students. So those of you who are students here today, I really encourage you to use this opportunity not only to listen, not only to learn, but also to ask questions, ask hard questions, to test assumptions, to really help us think differently about the work that we do. All students here at Nazarbayev University, whether they intend to major in literature or political science or sociology or engineering or medicine, all undergraduate students undertake mathematics as a compulsory part of the core curriculum. Because what we want to do is give students multiple mindsets when they enter the workforce or research. We want to make sure that they can use a range of different problem-solving tools to solve the complex problems that they'll be faced with. Our students, and we've got volunteers here in the red jackets, so please wave the volunteers, you'll find they are multilingual. They're multilingual certainly in Kazakh, English and Russian, but you will find many of them are multilingual in the language of mathematics as well. Many of them are mathematics majors, and they're here to listen, to learn, and to engage in the spirited dialogue that's ahead of us. As part of our commitment to this conference, Nazarbayev University is proudly providing 100 full travel grants for young mathematicians from around the world to attend this particular Congress. We see this as an investment in the future. It's an investment in the next generation of talent, and we want to work with ISAC to build bridges across the globe, across generations, and across different aspects of the scholarship of mathematics. As we know, all of you know this, mathematics is not only the foundation of science, but it's also the foundation of human progress. It's mathematics that helps us understand innovations in medicine. Mathematics fuels precision engineering and architecture and space travel. Mathematics underpins the algorithms that are really behind the financial system and modern economies. From modelling climate systems to improving supply chains, from designing safe transportation networks to optimising public health interventions, mathematics gives us the tools we need to solve the complex challenges of our time. Here at Nazarbayev University, we believe a mathematically literate society is a society that's better equipped to build a resilient economy, to drive effective infrastructure and equitable healthcare. So as we begin this wonderful conference and this exchange of ideas, it's worth noting some of the great thinkers that have led us to this point. As you would know, I'm sure, last century the great German mathematician Emmy Noether was given a beautiful obituary by Albert Einstein in the New York Times in 1935. Albert Einstein looked at the breadth and the depth of her work over many years, over 3 different eras. And in his tribute in 1935, he said, "Pure mathematics is, in its way, the poetry of logical ideas." And that's a very Einsteinian thing to say, someone who believed that even very complex phenomena can be reduced to something that's simple, not too simple, but simple enough to be understood and to be shared. And I think Einstein's words remind us that mathematics is not only about structure and certainty, but it requires imagination and elegance and simplicity. And I think the wonderful work of the late Mariam Mirzakhani, the first woman to win the Fields Medal, I think has been a great way to think about how we can accelerate to a new golden age of mathematics and scholarship. And one of her quotes in 2014 is very familiar to many of you, I'm sure. After thinking about the journey she'd been through to win the Fields Medal, she said, "The beauty of mathematics only shows itself to more patient followers." And it's a reminder that mathematics is not necessarily easy. It requires a great deal of precision, a great deal of practice, a great deal of hard work. But it's also a reminder of the value of persisting in exploration, to explore deeply and to embrace complexity with courage. And of course, Katherine Johnson, whose calculations helped the early era of the space age, was famous for saying, "We will always have STEM with us. Some things will drop out of the public eye and go away, but there will always be science, engineering and technology, and there will always, always be mathematics." So I do offer an encouragement for all of us who are here over the next few days to take full advantage of the opportunities that are here, particularly to ask the hard questions, to be unafraid to challenge assumptions, to test boundaries and to follow ideas where they lead, even into new territory. And particularly for the students, whether you're a doctoral student, a master's or an undergraduate student, raise your hands, engage with speakers. This conference, as I said, is not just for listening, but it's for you to probe and debate, because your questions matter, your voice matters. Use your ideas, test your ideas, and see what happens. And in that spirit, it reminds me of a quote from David Bohm, the great physicist, which was described at length in one of my favourite books by Peter Senge, The Fifth Discipline. And David Bohm is described as defining the difference between discussion and dialogue. And in his view, in discussion, we can fall into the trap of defending our views. It's a bit like ping pong. I say one thing, you say another thing. We bat our ideas across the table. And it comes from the Latin root, which is similar to the words for concussion and percussion. It's a clash of ideas. But David Bohm's view of dialogue is something very different. He refers to the Greek root of duo logos, contributing to a pool of shared meaning. And David Bohm says, in dialogue, we suspend judgment. We listen deeply and we explore new ideas together, because dialogue invites the collective intelligence of the group to emerge, to be something greater than the sum of the individual parts. So obviously, as we look to the future, we cannot ignore the rapidly expanding influence of artificial intelligence and how that affects all that we do in universities and elsewhere. It's no longer just a tool for computation, but it can be a collaborator in mathematical discovery. From exploring complex proofs to generating new conjectures, AI has the potential, obviously, to reshape what we do and how we do it. And it's worth remembering, I think, the words of Mirza Khani about the value of patience. Although AI can accelerate some of what we do, we still need patience. We need the patience to take the time to make sure that it's accurate, that it's precise, that it's profound, that it's elegant. But this conference is a timely opportunity to reflect on how we might harness these technologies ethically and sustainably and creatively to extend human insight and accelerate the pace of discovery. So in closing, I would of course like to extend my heartfelt congratulations to all the people on the organising committee and the advising committee. Your program is outstanding. You are building a bridge linking continents, linking mathematical traditions, and linking generations of mathematical thought. You've done a great job in bringing everyone here today. And for my final words, let me remind you of just a simple phrase that we say every day here at Nazarbayev University. And it's a phrase we use when we welcome new professors, new students, new academic and administrative staff to the university. What we say is, in this university, there are no stupid questions. If you have a question, please ask it, because together we can all learn. Welcome to Central Asia, welcome to Kazakhstan, welcome to Nazarbayev University, and welcome to what I am sure will be an inspiring and unforgettable conference. Thank you.
Thank you, Loretta, for your wonderful speech and continued support. Now, our next distinguished speaker, guest, host, is President of ISAC, Professor Uwe Kehler. The floor is yours.
Thank you very much. Dear colleagues and ISAC members, I also welcome you all to the 15th ISAC Congress. It was already said that it's the first time this Congress is held in Central Asia, and in fact, it's only the second time it is held in Asia. And in fact, there's no more suitable place for holding it than in Kazakhstan, because here in Kazakhstan, we have a large community of our ISAC members, which were very active in previous congresses and so on. And I was always enjoying their participation, their influence, and also their inputs they gave. I'm also particularly happy to see so many young and new faces, and hope that everybody can use this time to find new friends and new collaborations. It's tradition also that we actually should say a little bit about the development of ISAC at this opening ceremony, and it has been already 2 years that it was held in Brazil. Now in these 2 years, we intensified our work, especially with the ICMAM community. We had a steady growth with a lot of new members. And in fact, you can all see we even changed our website to a more modern design, for which I actually thank Thomas Ligotsky and Vladimir Mityushev. And also, this is a time where we actually can honor young mathematicians, because it's also the time to announce the winners of 2 prizes which ISAC is giving at these conferences. The first one is our traditional prize, that's the ISAC Award, which is given to outstanding young mathematicians over the years. And it's my great pleasure to announce that we actually keep with our high standards, and this year's award winner is Elia Brouet from Italy. Unfortunately, I think he cannot be here at the opening ceremony, but nevertheless, I call Irene Sabadini to give the laudatio. He's coming. Okay. Then let me actually
I will do the laudatio on Thursday.
It's better to make it on Thursday?
Yes.
Okay, good. In any case, you already know the winner now, and you can enjoy that to see. So please come also to his talk on Thursday, where we also then give him the things. And the second award is actually a rather young award, which we gave for the first time in Brazil. And that award is the so-called President's Award for Young ISACs, which is directed to young and active members in our community. It's given now for the second time, and this year's award winner is Duvan Cardona from Belgium, or should I rather say currently Belgium, originally Colombia. And for this one, I call now Paulo Sergeiras to give his laudatio here at the opening ceremony.
So, ladies and gentlemen, so Duvan Cardona Sanchez is a young Colombian mathematician who began his career with a first degree at Universidade del Valle, Cali, Colombia. He has obtained his PhD in the Ghent University under the supervision of Michael Rojansky and Julio Delgado, with the thesis Contributions to the Theory of Pseudo-Differential Operators from Compact to Graded Lie Algebras. Now, from 2023, he has a grant from the VWO Research Foundation of Flanders. This is a rather competitive grant, and that he obtained it first place, and now is postdoc again in Ghent. He was selected as Young Researcher Alderberg Laureate Forum in 2020 and 2021, and also has obtained a Global Minds Fund International grant from Ghent University in 2023 and 2024. Now, Duvan contributions cover a broad range of mathematics from harmonic analysis, partial differential equations, pseudo-differential operators, Fourier integral operators, and control theory, among other areas. He has publications, more than 50 publications, in journals like Compte Rendu de Mathématiques, Mathematische Zeitschrift, I'm a disaster for reading German names, International Mathematic Research Notice, and other similars. And most important, he has benefited in 2024 of a travel grant to work in UCLA with Terence Tao. He is extremely active in organization and dissemination of activities through ICMAN. He was president of that society and is, if I'm not wrong, vice president now. And in conclusion, Duvan Cardona Sanchez represents the unique combination of work and dedication to mathematics, and is fully embodied the spirit of the President Award for Young Scientists of ISAC. So,
well, with these ones you can see our community is still continuing and growing, and I hope it will continue in that way also in the future. There will be, for the ISAC members, an announcement that we currently are having to review a little our constitution after 15 years, and later on this year we will all ask you to vote on the changes. But that will be also later announced, and we will simply see that one. For the rest, I only can say that I wish you all a wonderful conference, and I hope You can enjoy the talks, you can enjoy the things. You can also enjoy this wonderful place. If you see, there are a lot of places where you can actually just sit down together and have some discussions or just enjoy your company. So I hope you can enjoy this wonderful university and this nice organization and just have a nice time, so that on Friday you can all say it was a nice time, nice spent. Thank you very much for all coming here, and let's wish us all a wonderful conference.
Thank you, Uwe. Thank you, Paula. Congratulations, Ilya, Dovan. Now we start our morning session for plenary talks. Our chair is Professor Nurlan Dairbek from Institute of Mathematics and Mathematical Modeling. Yeah, now.
Okay, hello. So I'm glad to open our plenary session. And our first speaker is Alexey Nazarbayev, IMPA, Brazil. And the title of his talk is Spontaneous Stochasticity.
Good morning. So it's a great pleasure to come and great honor to participate in this prestigious Congress. So let me say a few words in Kazakh first. Assalamu alaikum, kurmeti Kazak yeli. Менин акем Казахстанда дүниеге келген. Мен осы әсем елмен ерекше байланысты сезінемін. Шақырғаныңызға рахмет, бұл мен үшін үлкен мәртебе. I didn't prepare the full lecture in Kazakh. So what I said is that my father was born in Kazakhstan, and I actually have been here many times when I was a child. So I have really strong connection to this beautiful country, and it's a great, great pleasure to come here again and to see how you develop and grow here in Astana, where I've never been. So my cities were Almaty and Kochetav, and it's a great honor for me to take part in this conference. So I'm coming from IMPR. So let me just... So I'm here probably, right? I'm coming from IMPR, and so this is our institute. That my pointer is not strong enough. So that's just me to use this opportunity to also invite you to our institute, which is this building in the forest of Rio de Janeiro, and we have a very active visiting plan for visitors, especially in summer school, so which is January, February. So I think that's a very nice period for summer from this part of the globe. I come from area of turbulence, and we will be discussing this aspect of spontaneous stochasticity. So this concept comes from this relatively quite a recent point of view that on solution and on a concept of predictability, that appeared in the area of turbulence, and which has a very strong connection to the different fields in mathematics, which is partial differential equations, dynamical systems, analysis, stochastic process, and so on. So I hope that my lecture will give you some ideas, and maybe you will get interested in developing something in this direction. So the concept is very new, and that's why the lecture will be a mixture of physics and mathematics. So I will start with really stronger physical introduction, because this is important to understanding what is going on and what means spontaneous stochasticity. And then we come to some more mathematical developments in the direction. So first, let's see some videos. This is video from YouTube. So partially it anticipates the coffee break, but at the same time it introduces phenomena that we're dealing with. So when you put the milk in the teacup, you see turbulence. Essentially, turbulence is everywhere around you. In the air, in the water, in the ocean, and in the cup of tea. The only problem, you don't see it, because air is transparent. What is transparent? So when you put the milk, it's essentially just to see it. It's there. When we put the milk, you have a contrast, so you see the phenomenon. So the question is whether we can predict what you see. So how to predict? And I will start directly with physical model, and this is a model which, at least on theoretical level, contains all the necessary the ingredients. So essentially, if you want to model the flow of fluid, the usual way how you proceed, you start with the flow in the periodic three-dimensional domain. Periodic, it just means that you consider the flow in a cube. And cube has a periodic boundary. So whenever fluid flows through the boundary, it enters from another side. Or mathematically, you can say that it's flow on a three-dimensional torus. This is typical idea in order to avoid the physical boundaries, because physical boundaries just increase complexity further on. So we just consider essentially flow without a boundary, which is described by velocity field u depending on position x in 3 dimensions and time, and it satisfies this equation, which you can call it fluctuating Navier-Stokes equations. So the left-hand side is the first 4 terms is the Navier-Stokes equation. So du dt plus u grad u is inertial term. Then there is minus gradient of pressure and plus Laplacian of u, which is viscosity. And if you are used to Navier-Stokes, usually you have gradient of u multiplied by nu, which is viscosity. And physicists like to put the dimensionless form, so it will be inverse of a Reynolds number. So this red term is a viscous term. And then there is a fourth term, which is the last one, f. And here the fourth term will be deterministic. And finally, the green term, it's noise. So as you can infer from the title, so the spontaneous stochasticity, the phenomenon has something to do with stochasticity. So this is a stochastic term. So now, for those who are familiar with the field, what I should stress is it's not a forcing term. So it's often it's typical in the field of turbulence to consider the random forcing. So it's not a forcing term. It's just a microscopic noise term which is always present in the dynamics. So it's just a noise which exists because fluid is made of molecules. So there is very, very tiny amount of noise which is present, and it has a form of some coefficients, gradient of the psi, and psi is a tensor, so it's 3x3 matrix, which is a Gaussian field, delta correlated in space, delta correlated in time, then with the prefactors, which is just built up with, on the physical grounds. And you can find this term, for example, in Landau-Lifshitz fluid dynamics in the first edition. So this is, and the second equation is incompressibility condition. So this equation would be good description, but this equation is mathematically a nightmare because you cannot make sense of it. At the same time, you can make sense of this equation by using another idea of another physical fact is that the fluid dynamics is actually a macroscopic description of the fluid, so it's not valid at very small scales. So the scale of molecular, size of molecular, you don't have any more the continuous equation. So what you can actually do, you can make a Fourier cutoff at very small scale, so it means very large wave numbers, which means that you just say that Fourier components of the velocity field for wave numbers bigger than 2 pi over delta, where delta is microscale, are 0. So whenever you do this, everything becomes nice. So you can put initial condition, and then the whole problem becomes well-posed problem for a system of stochastic differential equations. So it's just a very, very large system of stochastic differential equations, which is perfectly well posed, and you can solve. You can find the solution. The solution is, of course, will be a stochastic process because there is the stochastic term in the equations. So mathematically, everything is good from now on. The problem is that from practical point of view, this equation is you cannot use them because no supercomputer can compute them. So what you do, you know that there are small parameters in this equation. And not just small, but they are extremely small. So all parameters that enter into the equations, all physical parameters, are very, very small. So if you think of this system as describing the dynamics of air on top of the Earth, just what's called atmospheric boundary layer. So it's motion of the air which is affected by the surface. Air around buildings and so on. So you think about like kilometer size, 3 meters per second. So you have all these 3 parameters that enter is 10 minus 8, 10 minus 38, and 10 minus 10. So nothing. And just compared to cup of tea, which is much smaller size of the cup of 10 centimeters, the speed is much smaller. I put this estimate, so the parameters will be 10 minus 4, 10 minus 19, and 10 minus 3. Still very, very small. So when there are 3 different terms with very small parameters, and these are problematic terms, the first thing you want to do is to remove these terms. Right? So if these terms multiplied by 10 minus 8 or 10 minus 38, this term can be negligible in some sense. And if you neglect these terms just formally, just put all the parameters to 0, you end up with classical equations, which is a Euler system, so Euler equations for the incompressible ideal fluid. So this problem, but unfortunately, this problem is most likely ill-posed. So we don't know this exactly. So there is a open problem of it's still quite not a problem if this problem if there is a blow up in the Euler equations, but from many point of view, at least from all practical observations, this problem seems to be ill-posed. So then, if you cannot just put parameters to 0, what we learn from partial differential equation that instead of putting them to 0, you can take a limit of these parameters to 0 and see if this limit converges. So the traditional interpretation of this limit, which we call ideal limit, is to consider the limit of these three parameters tending to 0 in sequential form. So the first, you take noise. You take a limit of vanishing noise. You send theta to 0. This is logical because theta is the smallest parameter. It's like 10 minus 38. So whenever this is a very well-behaved limit. Theta goes to, so what you obtain in the limit is just noise term will disappear and the final equations will be truncated, Fourier truncated Navier-Stokes system. So from very large system of stochastic differential equations, you obtain a very large system of ordinary differential equations. The next step will be removing cutoff. So it means that this microscopic scale can be sent to 0. This also, well, relatively nice limit because in the limit you get the Navier-Stokes systems, and we know that whether the Navier-Stokes equations are well posed or not is still an open problem. So that's millennium problem. At the same time, for physicists, it doesn't seem to be a big obstacle because we actually never see any problem with Navier-Stokes equations. So no observations which show that Navier-Stokes equation can blow up and do something strange. So we can still be okay. And then we come to the last problem of sending viscous parameter to 0. And here we have a trouble because there is no sign of convergence whatsoever. So you increase Reynolds, you decrease inverse Reynolds or increase Reynolds number, the viscous term goes to 0, but solution just get met. So you change a little bit. You take different Reynolds number and you get absolutely different solutions, at least on numerical grounds. So this limit just doesn't work. So actually the problem in this traditional interpretation is not the last limit, but the first limit. It's long was noted in different forms that you actually cannot remove noise from this equation, even if the noise is very small, you cannot remove it from the very beginning. And here I just quote some of rather many studies which tell about this. So we can start from the second one. So the paper by Ruel in 1979, who essentially talked that, who discussed that thermal fluctuations are very small and don't produce substantial deviations from the equations. So it seems that in equations of motion, these terms are small, but at the same time, they indicate they have large macroscopic effect after a relatively short time. And this is based on the observation that when you take the limit of this viscosity going to 0, the Lyapunov exponents diverge. So we expect infinite Lyapunov exponents. So there is in this limit there is a very, very strong sensitivity to any noise. And the other quote is from Lawrence, which is 10 years earlier, 1969, who was studying, essentially he was studying kind of toy model for the Euler equations for turbulence from perspective of the weather prediction. And he said that some formally deterministic systems, which would be Euler equations, in this system, if you have, if you start them, so if you start the system from the two states which are which differ by small error, they evolve into state. They develop a large separation after some finite time, and this finite time cannot be lengthened by reducing the error. So even if they're very, very small, after a certain time, the solutions separate. And even if you reduce error, this time when the solutions separate cannot become smaller. And which directly means that it's not a deterministic chaos, as we used to. Because in deterministic chaos, the error grows exponentially in time. It means that at least on a formal level, you can, by reducing the initial error, you increase the time in which you can predict the solution. So here it's different. So now we come to the concept of spontaneous stochasticity, which is formulated here as a conjecture. Actually, the formulation of spontaneous stochasticity is coming from different numerical simulation and simplified models which were studied in the last few decades. And this concept is evolving. So I was trying to formulate it in kind of a way how I understand it now. So idea is that you can change the way how you take a limit from the original well-posed system to the Euler equations in such a way that the limit will exist. And one of the ways is, instead of considering sequential limit, where the first limit was sending noise to 0, you consider the joint limit. So you send to 0 all terms together. So you send to 0 viscous terms, the inverse Reynolds. You send to 0 noise term as a power of Reynolds, and you send to 0 cutoff. So at every moment before the limit, we have the well-posed problem, and all the terms disappear together. So the conjecture of spontaneous stochasticity is that these 4 properties hold. First is that the solution converge, which is most important. We do have convergence. Unlike the previous situation, we do have convergence, and we see this convergence in this limit. And remember that at all before the limiting point, it's stochastic differential equation. So it's essentially the solution to the problem is a stochastic process. So the solution converges in distribution in this limit. So this is first point. The second point is that the limiting dynamics is not deterministic, but remains stochastic. So you take a limit of different terms to be 0, including the noise term. So you send the noise parameter to 0, and you still remain stochastic at the limit. The third property is that the limiting process, which is, as I said, is stochastic, it actually solves Euler equations. So essentially, its realizations are weak solutions to the Euler equations, to the initial problem for the Euler equations. And this supports the name of spontaneous stochasticity. So it's stochastic, and at the same time it's spontaneous because actually in the limit it solves fully deterministic problem. So you have deterministic equation, deterministic initial conditions, and it's solved somehow by the stochastic process. And most mysterious is the last property, is that the limit is actually universal. It doesn't matter certain extent. Of course, how you take the limit, so for example, how you take these parameters beta, gamma, or which noise you use, it seems that the limit is the same. So you need noise to have a limit, but what noise, the limit does not feel what noise was. So there is so somehow the limit is actually some intrinsic property, or the limiting stochastic process, intrinsic property of Euler equations themselves. So this is a physical interpretation of the concept of spontaneous stochasticity. Of course, I think you should be very unsatisfied with all these statements because they're very far from any close mathematical meaning. And I will not even try to do anything more precise because we don't understand many aspects in this formulation, and I think that whenever I give any answer, it will raise 10 more questions. So what we better do is we now move from the full description, which is fluctuating Navier-Stokes equation, to toy models. And we try to build a model which is completely tractable, so which carries all the properties of what we have here. Well, not all, carries some properties which we observe in the turbulence. At the same time, we can solve. So that will be a mathematical part. That's not the very last version of my talk. So I just want to mention that this part is a joint work with Artyom Raibekas also from Rio de Janeiro. Okay, so what is turbulence? How the physicists describe, so how we want to build toy model. So first of all, we have to see what turbulence is. Turbulence is usually seen phenomenologically as a collection of vortices. So you have a large vortex, like in atmospheric boundary layer, the largest vortex is size of kilometer. And then there are smaller vortices on the size of 10 meters, 1 meter, 10 centimeters. And it all goes down to 1 millimeter in atmosphere. So you have a collection of many vortices of very different sizes, from 1 kilometer, 1 millimeter. And then a dynamic at every scale, is chaotic. So you have a huge chaotic system. And then you want to take ideal limit. And the ideal limit in this situation is taking the smallest scale in these dynamics, which is millimeter in reality, and send it to 0. It means that at the limit you have infinitely many scales which all active in the dynamics. So this, in the limit you have a complicated system. So how you can make a toy model out of it? So let's just take some of the vortices of different size and build up equations which describe their motion. So what you do, we need many scales. So we take essentially we take vortices of sizes which go down to 0 as a power law. So first we take a vortex of size 1, next vortex size 1/2, 1/4, and so on and so on. So you have this sequence of vortices. Each vortex has its own turnover time. So the time in which the vortex will make a full turn. And also these times are getting smaller. The smaller vortices, they turn faster. So the simplest way to do it is to assume that the turnover time also goes down as a power law, and let's take it with a power law of 2. So the vortex of size 1 make a full turn in time 1, vortex of size 1/2 make a full turn in time 1/2, and so on. And now what we will do, we will follow the kind of Poincaré idea to consider the system in discrete times. So only in Poincaré, with the Poincaré map, you can consider the change of all variables of the system in finite intervals of times. Here we cannot do it exactly in that way because we have different turnover times. So what we do is that we consider dynamics of the largest vortex in a discrete times of its own turnover time. The next vortex will be considered in its own discrete time. So at the end you get this lattice where this is space-time. So the vertical axis is just numbering the vortices. So the scale 0, scale 1, scale 2, and so on. So L1, L0, L1, L2, L3, and so on. And the horizontal axis is time. So as you see that the largest vortex is discretized in time with step 1. The next vortex is discretized with space with step 1/2, 1/4, and so on. So at the end you get space-time in such a less typical form as a fractal lattice. So we're considering the dynamics on a fractal, where the space-time is represented by a fractal lattice. So this is just a configuration of the system. So next what we have to do is to define dynamics. So we should define dynamics, and we know that from fluid dynamics that dynamical equations are self-similar, which means that we have to define dynamical law on this lattice, which should be the same at each cell. So each cell we should give some some law, and each vertex we should also put variables which describe the state of the vortex. So now comes your imagination. So we don't want really to build up the model which describe really motion of the fluid. We want to build up the model which has interesting properties similar to turbulence, but at the same time can be solvable. And remember that we have many vortices of different size, and we know that we need to have chaotic behavior at each scale. And this is very hard to do. At the same time, we know from dynamical system that there is a very nice dynamical system which has all the chaotic properties that you can imagine, essentially, and at the same time it's simple. And this is what's called Arnold-Cat. So this third line Arnold-Cat map is just a linear map from a square to a square. And essentially it's called Arnold-Cat map because it maps a cat to the picture which you see on the right. So this is a linear map defined on a torus of period 1 in each direction. So what we do, we say that each phase variable, so each vortex will be described by phase variable, which is a point on a torus. And then what you have here is with arrows is a definition of the dynamical system. So if you want to find the value at new node, you just take the values of the previous nodes, which are shown by arrows, and arrow is Arnold-Cat map. So each arrow is just transformation of the value of one node to another node through the Arnold-Cat map. When arrows meet, you just take a sum. So this is a fully defined dynamical system which defines the value at new time as a function of the values of previous time. So somehow you add initial condition, so you add values at time 0, and intuitively you're good. So intuitively you think that, okay, now you can find a solution because every value at any time can be expressed through the values at previous times. These values can be defined as values of previous times and so on. So in fact you can solve the system, but in fact you don't. And the first statement that you can prove is actually this system has, for any initial conditions that you put, it has infinitely many solutions. So the theorem is the following. So whatever initial condition you put at time 0, you have infinitely many solutions, and these are solutions which are obtained by putting arbitrary numbers at red nodes. So at every red node, you can just put any number, and then at all other nodes, which are black and green, you can define the values uniquely. So in some sense, you have infinitely many solutions, and the reason why you have infinitely many solutions comes exactly from the fractal structure of the lattice, because try to trace back any value in time. So you have to go through, in order to define a value at any node, you have to go follow the arrows backwards and see where they go. If this line of arrows going backwards comes to the initial condition, so comes to the left side, you know the value. It comes from initial condition. But there are infinitely many ways how you never reach the initial conditions. So if you go from each node to the left, there are infinitely many ways which just go down to infinity. So that means that even though you have a deterministic way how to define the value at any time in terms of the values of previous times, these values are not defined by initial condition in general. And this is a proposition. So you can solutions are non-unique, and the good part of the system is that you can find all of them. you can find all of them, and not only all of them, you see how many. Essentially, half of the dimension is arbitrary. And this has a rather close connection to recent developments in Euler equations themselves through the what's called convex integration method, which was developed very much in the last decade, where it was possible to prove that Euler equation has actually has strongly non-unique weak solutions. So this is just a toy model which shows exactly how non-unique they can be. Okay. So if the solutions are non-unique, what we do, if you remember the differential equations, including, for example, Burger's equation, you add regularizing term and start to send this regularizing term to 0, trying to select the true solution. So this is, by the way, the kind of concept which we learn sometimes, often in partial differential equation, is that if the problem is ill-posed, it is ill-posed because the model is not good enough. So we should add regularizing term, making this problem good, and then try to see the limit of this term goes to 0, which will select the right solution. So let's try just to do the same procedure here. So how you make a regularization? We want to have a regularization and noise. So what we do here is very natural. So you just make a cutoff. You say that our system is just 0 below a certain scale. So you check, you take n, the number of scale, and for n bigger than n capital, you just put zeros. So you take this lattice and cut it from below. And also we need noise, so you just put at this last level where you cut, you add noise. Noise means that you just put at every node the random number. So IID random numbers, which is important, that it should be absolutely continuous random numbers. So now, as you made this cutoff and put random numbers, system becomes well-posed, and you have unique stochastic solution of the initial value problem. So problem is nice, essentially because whatever arrow you follow backwards, you either hit the initial condition or you hit the cutoff. So you're fully, so in short, the value at every node can be written explicitly in terms of the initial conditions and the noise. So now solution is unique, but solution is a stochastic process. So we will, from the very beginning, I said that we will consider convergence in distribution. So essentially, what we are interested in is a probability measure, which describes the solution. So we have a unique probability measure, which we call mu n, and it's a probability measure in space of fields. So it spells in the space of the product, the product of space of all nodes. So that's we have a probability measure which describes the solutions of the system with noise. And what we do next is we take this cutoff to 0. So taking cutoff to 0 is essentially the same idea as taking the limit of all these parameters to 0 in fluctuating Navier-Stokes equation. So this is so if the previous situation was analog of Euler equation, so this new system is analog of a fluctuating Navier-Stokes, and we want to take a limit when the regularization goes to 0. So this cutoff goes to infinity, and formally this regularized system becomes the ideal system on the slide before. Okay, so what means spontaneous stochasticity here? So whenever you take a limit of the cutoff going to 0, you end up with fully deterministic system. So there's no noise anymore, because noise just disappears down. You have all relations deterministic, you have deterministic initial conditions. So spontaneous stochasticity is a situation when the limit exists, so the measure which describes our solutions at the regularized system converges to a certain measure, mu, and this measure remains stochastic. So it's not a Dirac measure. So you have a limit, but limit remains stochastic. So you can prove this theorem, and theorem tells that the initial value problem for any initial condition has a spontaneously stochastic solution, and the limit of this with a limiting probability measure mu, which we will specify now, and this limiting measure is universal. It doesn't matter which noise you put. So whatever noise you put at the cutoff, you have a limit. Limit is stochastic, and it doesn't even care what noise was used in the regularization. Okay, so what is this measure is? So there is a formula, but it's actually easier to say that it's a uniform measure of all weak solutions that we obtained before. So the measure that you can that you obtained before is just a uniform measure on all the solutions. What means that you take a uniform measure on the red dots, and then all the other dots are defined uniquely. So somehow we have fully reproduced spontaneous stochastic picture here in the following sense. So first, we took the regularized system and considered the limit of regularization go to 0, it converged. So convergence first. Second is the limiting process, the limit remains stochastic. So even in the limit we have randomness. At the same time, the limiting measure is fully supported on non-unique solutions of the deterministic problem. So the limiting measure is actually solving fully deterministic problem. And fourth is that it's universal. It doesn't care what noise is, but so the limiting measure is independent on the way you consider regularization. So here you have example of anti-selection. So we use that if you take ill-posed problem and at regularization take limit of regularization goes to 0, you select a good solution. So this example shows that there is situations that when instead of selecting a good solution, you actually don't select anything, and it has full physical meaning. So what you get in the limit is that you select any solution with equal probability. So this is a model where you can, which is ill-posed in a limit, and whatever regularization you put with noise, and take a limit, you will select any solution from the pool, so from infinitely many possible solutions with equal probability. And this is something what we expect from, similar to what we expect in spontaneous stochasticity for turbulence. So this is just a picture. So this is a picture what happens. So certainly this is very simple toy model, so which is built on very simple elements, and this is how it behaves. So each cell is a torus. So you think that each cell is a torus. So you start with the initial condition, which are just dots, so that each cell shows the probability distribution. So initial conditions are deterministic. So you have Dirac measures. So you have dots. Then at one step in time, it's still deterministic, and the next time they become random, and not actually random. They each separate variable become uniform distributed. There is correlation between them, but if you just take any one, it's completely uniform. So this is behavior of the system in any regularization limit. I think I have still a little bit of time to address the proof. So the proof is rather elementary, and it's all built on the ideas from dynamical systems. So what we need to prove is that the regularized measure converges to the uniform measure, Haar measure, and then essentially it's based on a lemma. So I didn't say. So in mathematical formulation of the theorem, we consider the product topology on the lattice and the weak convergence for the measures. So essentially, what you need to prove is that there is a weak convergence of any finite dimensional marginal for the measures. So this is equation A5. So you have to prove that any finite dimensional marginals converge. Then for finite dimensional marginals mean that you only need to prove that the probability distribution converges for any finite number of vortices. And for this finite number of vortices, you can find solution explicitly. Well, at least you can write a formula, and so you can write a formula for the value of the solution of every node in terms of initial conditions and in terms of noise terms. And then you find out that you're lucky enough that if you take if you take these nodes, you can number them in such a way that the noise term come with prefactors, and the ratio of prefactors goes to infinity when n goes to infinity. So essentially, all these constructions, it allows you to prove the statement of the lemma A5 just by expanding the test function in Fourier series and then using Riemann-Lebesgue lemma. So it's not something very complicated, but it's very strongly built on the fact that the Arnold cat map is linear. So the fact that Arnold cat map is linear allows you to find solution at every node, and then it allows you to study the limit. So it means that whenever we add any non-linear interaction, there is no way to extend this, to generalize this proof. The linearity of the system was essential. We don't know what to do if the system will not be linear. Okay, so what we have up to now is that we have a toy model where we can regularize the system, take a limit will exist, and it will be spontaneously stochastic. So now the next question, at the same time, this is a very special toy model which is built on linear maps, which are chaotic, but they're linear. So what happens if the system becomes non-linear? So for example, instead of the interaction with the Arnold cat map, you put some non-linear function. We cannot prove it, but you can make numerical simulations very easily and see that spontaneous stochasticity is there in exactly the same form. So you do have a limit. Limit is stochastic. It's not any more trivial. So it shows some stochastic dynamics. At the same time, it's also universal. Whatever noise you put, you get exactly the same picture. So now there's several questions which arise: is why spontaneously why stochastic solutions converge at all at ideal limit? Why, when you take the limit of regulation goes to 0, why they converge? What makes them converge? The second question is why they remain stochastic even though the limiting problem is formally deterministic. Well, this second point is more or less clear from the toy model. Is the limit in principle can be stochastic if the limiting problem has infinitely many solutions, right? Because there are infinitely many solutions. So in fact, in the limit, you can, if the regularized system was stochastic, the limit can just put certain probability measure by telling what is the probability of selecting any of the non-unique solutions. And the hardest question is why the limit is universal. So why there is no dependence on the regularization and noise. So, kind of, by the way, kind of thing you know, because if you remember the limit, implicit limit in Burger's equation, the limit will be the same whenever you take a viscous term or substitute the viscous term by any other dissipative term. You will still have the limit with the weak solutions with the shock waves. So the limit will not depend on regularization, and here it's even worse. So it doesn't depend on regulation and noise. So why? So in this picture, I tried to give an idea in a very short form of this, of the construction, which is called renormalization group approach. It's essentially follow the ideas of the mixture of the renormalization group approach developed by Wilson in statistical physics, or by even more closer to the approach to the theory of Feigenbaum in dynamical systems, so the renormalization group. So what it tells is that let us consider the dynamics on a lattice in terms of a flow kernel. Flow kernel is just transitional probability. So given the initial state at time 0, what is the probability to go to time 1? Which state you go at time 1? So this is a flow kernel. And the full dynamics actually of the regularized system is defined by the flow kernel. If you know flow kernel, you define all the rest of the dynamics. So what it turns out that if you have a flow kernel of the system regularized at level n, you can define a flow kernel of the system regularized at level n plus 1 for the explicit relation. And this relation comes from the fact that actually the all dynamics is self-similar. So if this blue piece describes the dynamics regularized at scale n plus 1, then the red block has just the same structure as the full system. So the red block is just repetition of the full structure, but regularized at scale n. So regularized at scales 1 level larger. Which means that if you want to construct the flow kernel at scale n plus 1, what you have to do, you can write this relation where you have to use twice the flow kernel of the system regularized at level n, and then also add the green block on the top, which is missing interaction at the largest level. So anyway, I probably cannot give the full detail, but what is important is simply that we can represent the limit of regulation limit as a dynamical system. So whenever you regularize system at scale 1, the L1, the kernel of the system regularized at scale L2 is just a function of the previous. And when you want to go to the scale L3, it's just a function of the previous kernel. So putting this cutoff n lower and lower is just exactly the same as applying the explicit transformation, which is called this curved R, on the flow kernel. So, in other words, the regularization limit just becomes a dynamical system. Only it's a dynamical system in a rather unfriendly space. So it's a space of kernels, of probability kernels, but it's a dynamical system. So, in other words, so the existence of the regulation limit now is translated to existence of the attractor of the RG dynamics. And the limiting system is just described by this attracting point. So this is exactly what happens, and actually the proof of the R0 spontaneously R0 cat map system just tells that in that system the renormalization group dynamics has a global attractor fixed point, and this attracting fixed point is this uniform measure on all non-unique solutions. At the same time, we automatically get all the rest. So whenever you have an attracting fixed point, so what is important is that in this dynamics, you have two pieces. A renormalization group operator, so operator which describe dynamics, and it depends only on the limiting ideal system, and you have initial condition to these dynamics, and initial condition is fully defined by regularization. So that's why the limit does not depend on regularization, because regularization only defines the initial flow map. And while the limit is, if the limit is attractor, it doesn't remember from which point it comes to. So that universality of the spontaneous stochasticity becomes very, very natural. Okay, so I'm coming to the conclusion. So essentially, what we understand now is that, first of all, we have a conjecture that the formally deterministic Euler equations, the initial value problem for the Euler equations, has a spontaneously stochastic solution. So if you want to solve Euler equations, these Euler equations, it will be solved by stochastic process, despite the system is formulated fully in a deterministic way. The way how you do it is you add the regularization, and it's crucial to add not only viscous term, but also to add noise term, and in the joint limit, you get the joint limit will converge, and will be universal. Okay, this is, as I said, only conjecture, and however, we have more and more evidence that it's true from different perspectives. At the same time, this whole scenario can be proven rigorously for toy models, for some very simple toy models. And we have some ideas how to extend it for other toy models through this approach for renormalization group. So there is kind of there is initial stage of the theory which is supporting all the things. I have time for. Let's first better instead of looking for further developments. Let's look at the video again. If you can you put the video once again? Okay, so that's also for coffee kind of, since I'm taking your time from coffee break. So yeah. So what spontaneous stochasticity tells us about the motion of the turbulent flow? It tells us that the motion is actually not predictable in the deterministic sense at all, because the noise, molecular noise, which is there, which is completely tiny, it actually will give a completely different solution every time you repeat the physical process. If you start from exactly the same initial condition and you do it again, you will see completely different solutions. This is opposite to this video. The video just shows exactly the same evolution. So what you expect to have in reality, every time you put the milk in exactly the same way, you will have completely different process. At the same time, it's not a loss of just a loss of information. It's not just that we don't know how to predict. What we can predict is a probability. So there is a well-defined probability of how this process will evolve in time every time you do this imaginal experiment. So that's actually the concept of spontaneous stochasticity, and there is there are a lot of what we don't know, but it seems that we're in the we have some basis, so there is already some mathematical development, and I really recommend, including the young students, to put attention to this problem, because this is where you have the. It seems that we have some emerging field in which come across different fields of mathematics and physics. So thank you very much. So this is, I put a couple of pictures which from Rio de Janeiro and Astana. And thank you very, very much for your attention.
So my question is that you considered the equations on the two-dimensional torus, but why is it important for you on the two-dimensional torus instead of the sphere? And I didn't see the torus in the coffee cup, by the way.
Well, very good question. So essentially, when you go to the toy model, the idea was to find a solvable toy model. So the only aspect we want to keep in the toy model is the first that is the self-similarity of the original equation. So there is no physical connection whatever. And the reason why we use torus is because it's chaotic. So we want to keep chaotic element, and it's invertible. It's a map which allows us essentially to solve the system. So you don't have to think that this toy model describes physically any properties of the flow in
so just a mathematical convenience, right? Just you use the mathematical convenience of the torus.
Absolutely.
Thank you for your very interesting talk.
Other questions? Okay, let's thank our speaker again, and we have a break.
Colleagues, we had a very motivating lecture for coffee break. So it's in ballroom left, please. So every day at 11 a.m. we have morning coffee break. So it's in the room, it's close to here, from here probably. The ballroom left. because your
no
colleagues,
problem. Don't worry about that. That's
they have met
normal.
old friends and they
Yeah, in the
cannot-
forum, it's normal to come back
Okay.
sometimes.
I will do that all that.
Yeah. May I just get ready for that? So.
Please take your seats. We will start in just a few minutes. Okay, please attention. We are starting our next talk, and our next speaker is Gang Tiang, Peking University, China.
Thank you for thanks organizers for invitation. It's my great pleasure to be here, and to such a nice audience and very diversified audience. So anyway, this is my second time to this university, and it's always a pleasure to come back and for this wonderful and young university. So anyway, so today my talk will be kind of introductory talk. So I will talk about how analysis can be applied to studying a geometric problem or topological problem. So I will probably, I apologize, probably not including technical details. So the title of my talk will be geometric flows and their applications. So in geometry, at least we, at the moment, can I just use the, okay. So in this talk, I guess I have to use this, so it's okay. Which one? Oh, you have to turn it up. One. Hello? Oh, yeah, okay. So in this talk, I will always, in geometry, always consider space. We consider manifold, and we want to understand how this geometry of this manifold interact with topology or other things on these manifolds. So for simplicity, I always assume this space to be a closed manifold without boundary. Of course, you see, okay, why don't we consider things with boundary? Actually, that makes things a bit more complicated. So anyway, to make it simpler, so today I will not consider things. I will consider space without boundary. So giving a geometry on this space, by that I mean there's a Riemannian manifold, a Riemannian metric. So this is locally simply given by a positive definite valued matrix. So it's given by that. It's a metric, and for this metric, important quantity is a curvature. Okay, the curvature is invariant. Namely, is independent of how this metric is presented, but this measures how this space is curved. So it's an intrinsic quantity. Okay, for example, if you change your coordinates, this metric is represented by another matrix, but the curvature will stay the same. Okay. So let me start with a case we probably know much better, or at least many of you. So it's a case when M is a surface, or the dimension is 2. So the curvature is then determined by a function called the Gauss curvature, okay, a simple function. So on a given space, there are many geometry. So there are many metrics. So one of these things theme of today is to find a good metric which you can use it to study underlying space. So the simplest condition, so namely the one thing to make the metric nicer is to make a curvature as nice as possible. So I guess in the two-dimensional case for a function, the simplest function is a constant function. So we want to make a curvature to be constant, or in some sense, its space is homogeneized. Okay? Everywhere curvature is the same. Everywhere space is curved at the same rate. Okay? So what we can do is we can turn that into an analytical problem, into a PDE problem. So if we assume G0 is any given metric on M, we can have a new metric. Of course, this metric may not have constant curvature. The metric we start with may not have constant curvature, but we can do a conformal change. So then we want a new metric to have a constant curvature. So if you write down because curvature can be expressed in terms of derivative of a matrix, and you can, by easy computation or straightforward computation, you can derive this equation. So U is a conformal factor. U is a logarithmic conformal factor. So Laplace U minus K0. K0 is the Gauss curvature of G0. G0 is kind of arbitrary, okay? And the K is a constant. That's what we want to do. And you can have this semi-linear equation. So this equation have been studied a lot. I'm sure many people in the audience probably already know how to do this. And that's also when I was a graduate student at Peking University, as a master's degree student, we were studying this kind of semi-linear equations. And as a student in functional analysis or variational problem. Anyway, this equation is solved due to work of Nirenberg and many other people in the 70s. So in high dimensions, so the curvature tensor has more components. So we are led to consider a more complicated equation. One equation is called the Einstein equation. You know, as in the general relativity, the metric is simply gravity means metric. Okay, so Einstein equation is given by a so-called Ricci curvature, and of course today, or at least in geometry now, we are considering static solutions. So general Einstein equation should be a hyperbolic equation. So here we consider static solutions. So this become a kind of elliptic type. Okay. So here I'm not going to define Ricci curvature, and Ricci curvature is part of a curvature. So what's the meaning of Ricci curvature? Here is an intuitive definition in the red words. Measures how volume form is varies due to space is curved. Because if we do a calculus on a Euclidean space, of course the volume element is the same at every point. Okay? But in curved space, if you do an integration at different points, you may need to use a different volume form. So the Ricci curvature just measures how this volume form varies because the space is curved. Okay? And you can make that rigorous as a definition, but let's skip it. The approach to solve this Einstein equation is to use the Ricci flow, which was introduced by Richard Hamilton in the 80s. So Einstein equation is a system, and it's actually, even we consider static solution, it's not quite elliptic in the strict sense. There's a big diffeomorphism group action. Okay, so this caused difficulty in solving equations. So one method, there are many special solutions. For example, by gluing method and so on. But however, one method we have now, probably the only method, and so far is by Ricci flow. Okay, and actually, many years ago, people also tried to use a variational method because the Einstein equation is a variational problem. But so far, it's a difficulty to do that. At least the Ricci flow is more successful in many respects. So this is essentially a parabolic equation. So this is was local existence was proved by first by Richard Hamilton, then simplified by the talk. Namely, giving any initial 0, you can have a solution for up to some time. So there's a local existence. So let me recount back to a two-dimensional case. So in the 80s or early 90s, Richard Hamilton and some other people re-examined the problem I said before. So in the previously, I said this semi-linear equation of constructing a constant Gauss curvature metric was solved by Nuremberg and some other people. But however, that solution somehow used the geometry of underlying space. In fact, there's one way to solving that equation is you can use, for example, Riemann mapping theorem. Riemann mapping theorem tells you there is a constant curvature metric on any closed Riemann surface. So you can interpret properly and use that to get a solution of this equation. But now, I want to say, I change approach a little bit. I want to say I have a method and which I purely use analytical way, and without having any knowledge of underlying space, and eventually want to get a geometry. Okay, so this can be done by Ricci flow. So again, because of 2 dimensions so special, you can reduce the equation to a scalar equation. That's how we did over there. Okay, we still do a conformal change, and turns the Ricci flow is very nice. It preserves conformal structures. Okay, so you get these semi-linear parabolic type equations, and of course this equation is still to solve. Okay, so by reparameterizing t and shifting u by some constant, okay, you can get an equivalent flow, so-called normalized Ricci flow. So this normalization simply means how to determine that CT or so on is you want to make sure along the flow the volume is fixed, total volume is fixed. So you get this scalar flow, normalized flow. This flow is completely equivalent to the previous flow. It's just a different formulation of that. However, after normalization, one can prove, and I guess it was proved by Richard Hamilton, and it's actually not that hard to prove. So there's a global solution. Namely, for this normalized flow, there's a solution ut for all the t bigger or equal to 0. So moreover, as t goes to infinity, you can prove this gt converges to a metrical constant curvature on M. Constant curvature on M. So this was first proved by Richard Hamilton. One case, which is a constant, is 0 or negative. And then later on, the Banchur, also in the positive case, he did it, and some actual assumption on the initial metric, and this assumption was removed by Banchur. And then there was a small problem left, which I fixed. Namely, in this original proof, I used the underlying space when the curvature is positive. Use the fact underlying space is S2. So then the limit metric, it has a constant curvature. Okay, so it turns out this assumption can be removed. So upshot of that is, if you start with Ricci flow, start with any G0, you solve the Ricci flow, and you prove the limit exists after normalization, and the limit has a constant curvature. Okay? So this whole thing has, of course, you can say this result is already known many years ago, okay, by a different approach. But this approach has a new angle, namely does not assume any prior knowledge on the underlying space. So then you can use the very classical result, which says if you know it's a 2-dimensional space, and giving a conformal class, namely I change a metric by conformal factor, then if there is a unique constant scalar curvature metric, a constant Gauss curvature metric in a given conformal class, then the classical theorem, I guess this theorem is proved by rich flow or by previous theorem. And so then you know the space or the surface, the universal covering is the standard. Okay, is S2 or R2 or hyperbolic to plane. Okay, so this is called uniformization theory. So this way we get one. Let me summarize a bit. So I consider the purely analytical problem. I use the rich flow to get a metric of a constant curvature, then use the classical uniformization theorem to conclude that this surface is determined by a fundamental group, and the universal covering is simple. Okay? Of course, as I said, this is just a kind of reproof of Riemann mapping theorem, but here, this new way of approaching things is useful, and we hope this kind of approach can be generalized to other dimensions. So now assume M is a compact three-manifold, okay? And the static solution of rich flow are given by, I should say, static solution of normalized rich flow by Einstein matrix. Namely, the rich curvature is constant. In dimension 3, the Einstein matrix is very nice. It's very rigid. We know it was known a long time ago that if M admits Einstein matrix in dimension 3, then its universal covering is of the form S3, R3, or hyperbolic 3 space. Okay? So this is the same as two-dimensional case. Okay? And this is not true in higher dimensions. When the n bigger equal to 4, you might have Einstein matrix, you might solve the Einstein equations, but you cannot conclude the space, the universal covering space is like that. Okay? So in dimension 3, you have that in a way like two dimensions. And so then the question becomes, does M admit that matrix? In general, it's no. Okay, answer is no. That is the geometrization program. Geometric conjecture states any three-manifold can be decomposed in a natural way. Of course, today is the natural way. There are some mathematical terms. Okay? You can say along the incompressible tori and so on, but today I want to skip that technical things. So into an Einstein three-manifold plus some graph manifold. Huh? Like this? Yes. Okay, sorry. I should be close enough. So anyway, and this some graph manifold, I actually also have geometric structures. So that's called, so Thorsen classify into 8 kinds of geometry. So 3 of them are Einstein, have Einstein matrix, and others 5, in some sense, kind of degenerated. Okay, it's a kind of collapsed situation. So it's a kind of degenerate situation. So anyway, the Poincare conjecture is the case when the M is simply connected. Okay, of course we know the Perelman solved the geometrization conjecture by using the rich flow. Okay, so I briefly say what his real contribution is. So if a rich flow has a global solution, I should say normalized rich flow has a global solution, namely for all t bigger equal to 0. That's true in dimension 2. And also, so that's a first if, okay? Second if is if it converges to a smooth metric as t goes to infinity, then its limit metric is an Einstein metric. Of course, you need to prove that, and it can be proved by Ivey in the early 90s. So then the universal covering of M is is standard. Okay? So you have two if, which are true in the 2 dimensions, whether they are true in the 3 dimensions. A simple question as simple as that. Okay? Of course, we know it cannot be because we know not every 3 manifold has the Einstein metric. But one successful example, that was the first example of people got really interested in, which inspired the people in studying a Ricci flow, is Richard Hamilton did in the maybe now it's not 20 years ago, it should be 30 years ago. I don't know why I still put 20 years there. Time goes fast, okay? So if an initial metric has a positive Ricci curvature, then Ricci flow has a global solution, and this is true. So if you put some condition on the initial metric, and this is indeed the case. But in general, it's not. In general, it's not. So however, Ricci flow in dimension 3 develops singularities, and the singularity can be either forced by topology and caused by complexity of a metric behavior, even if a manifold has simple topology. Okay? For example, after many years ago, I was asked by some topologist, and asked a question, say, so I gave you S3. I know it's S3 manifold. Of course, the Poincare conjecture say it's, of course, I start with a metric which has a very large part of is negative curved, okay? And tell me how to evolve so that this negative part become positive and become a constant curvature. Unfortunately, I cannot, okay? And I still cannot, because it's Ricci flow is kind of parabolic equation, so it's like you put a heat source here, and after a while, the whole room become a constant curvature, a constant temperature. But if you ask how this evolving process goes, it's very difficult. Okay? But anyway, the Ricci flow tells you, and without explicitity, but tells you how it evolved to a homogeneous metric. Okay. So what one is because of singularity does occur. That means you cannot have a finite time. You cannot have a long-time solution. You have to encounter, have to study finite time singularities, so then we need to consider more general solutions called solution with surgery. So this you can regard this as a generalized solution for Ricci flow, but this is not is a refined generalized solution, because we do need to know how geometry evolves. Even a solution is not not smooth in a standard way. Okay. So anyway, so let me just not go into these details. So this is so this process is parameterized by an interval. So you basically have a cut time into intervals, so that each interval is a solution or standard solution Ricci flow. But from one interval to other interval, you have to encounter surgery. So you have to know how this space is changing. Okay, so they're called a surgery. And eventually the solution may not be on the same space, but we need to control how this space changes. So to be useful, one needs to control both topology and the geometry of this surgery process at a singular time, namely at a time when the Ricci flow encounter singularities. Okay, so for example, it's crucial for topological applications that we do a surgery only along the spheres. Namely, so what is the simplest way to do a surgery for three manifold? You cut along the surface and then reglue them in a different way. Okay, so the key point here is you want to cut along the spheres instead of a surface of high genus. Okay? And surgery along the two spheres produce a connexon decomposition, which is well understood. Namely, if you cut along the two spheres, topology it can be topology for the space before surgery and after surgery are well understood. So, but if you want to do a cut surgery, for example, along the tori, you might completely control the topology of three manifold, because there is an old theorem in the topology which says any three manifolds that closed can be obtained from a three sphere by doing a surgery along the tori, along the few tori. Okay? So basically what the paramount crucial contribution is to prove one needs to do a surgery only along the two spheres, and the change in the topology can be completely understood. Okay? Of course, there are many other technical things, technical details, in order to have a complete proof. Of course, the whole proof eventually become a few hundred pages. But this is a crucial point. Without this point, and you cannot go further. Okay, and so this is a breakthrough point. And actually, this point was already realized by Richard Hamilton. He also tried to do this. Okay, so he called the no little loop lemma. So after that, we can still say ask things like whether we can still do things as we did for surfaces. Okay, so I called refined geometrization of three manifolds. So this time, I just want to use a purely analysis, no priori knowledge from a topology and other things. Okay, and also I want to hold the process to be canonical. Even you go through a surgery, you expect the space after surgery or reach flow after surgery is completely determined or uniquely determined by reach flow before the surgery. So even you have a generalized solution called a reach flow with surgery, but this solution should be continuous, depends on initial data. That's the first thing we try to do in the differential equations, right? So, but Paramount didn't care about that. Okay, he only cared about topological things. So here we want to do everything is canonically determined, even finite time surgery. So namely, what we do is a reach flow give you a tool, which says they start with any three space, and you are strong enough, you are so analytical, so strong, you can analyze all the analytical surgery, you can know the models of finite time singularities, and then you flow along the flow. You reach your final destination. That's a space of a constant curvature. Okay, so it's like no matter what you start with, the final destination is the same. That's true in most cases anyway. So basically you formulate these things in like this. So this is this description. So there are finite many surgeries first. Paramount didn't do that. So and also I want to say each surgery become a classical solution. Okay, for large T. Right? And each GT become extinct at finite time. Don't worry about that, because that's sometimes you solve a Poincare conjecture, the reach flow become kind of trivialized. Okay, after finite time, or after proper scaling, the GT converges to a finite set of canonical metrics. Okay, and note and the prime factor connect some of those MI along the incompressed tori. That's a technical word, and you need to do a lot of things by using a minimum surface theory and so on. So the uniqueness of GT is amount to proving that any finite time surgery is canonical. By Paramount's work, topologically is canonical, the finite time surgery is always done along the tooth fields. But we do not know it is geometrically unique. It's still, I guess, at the moment, it's still unknown whether finite time singularity is canonical. Okay, and it's still a good question. And my former student Richard Baumler said once claimed he has some idea to do this, but so far it's still I haven't seen a solution yet, so it's still open. So, however, a few years ago, Baumler and Kleiner had found a way of constructing rich fluid surgery, which depends on initial data continuously. Okay, so it means it's a unique rich fluid surgery for any fixed initial data. It's solved that part one in a weak sense, but they didn't know, or we don't know yet, and the finite time singularity is canonically. Okay, but they somehow it's a complicated, very technical way to construct a solution with surgery so that the whole solution, even if it's a generalized solution, but it depends on initial data continuously. Okay, so this has applications. Okay, so you can see this talk I basically want to show you some of these analytical things since this analysis. So if we strong enough, we have enough understanding or regulatory theory about the equation we're considering, we can have interesting applications. So as an application, they proved that the diffeomorphism of a group of every three-dimensional spherical form, space form. So space form means S3 quotient by finite group. Yeah, because S3 is a unit sphere in a SR4. So its isometric group is L4, SO4, and this gamma is a finite group in SO4. Okay, so it's proof of generalized Mayer conjecture. So and more recently there is actually only and only last year or so on. It's this paper probably is it's being accepted recently. Is alternative proof was given by Haushofer and Catover by using minimum surfaces. Okay, but another kind of differential equations. So now I should remark the solution for original Mayer conjecture for S3, namely without gamma, was previously given by Hatcher. So this Baumler, Kleiner also gave alternative proof of that, okay, by using analytical methods. So moreover, in a surprising way, Richard Baumler proved the following things. I'm not sure this. This is in the series of papers. It's a long paper. There are only finite time many surgeries, which Paramount didn't prove that. Okay, and the curvature of GT is bounded by C over T. Basically, now after normalization, curvature is bounded after the finite time. Okay, and of course these things was conjectured by Paramount. Okay, so these results of Baumler showed imply after proper scaling, the GT converges to a canonical metric. So this canonical metric could be it should be an Einstein matrix and plus other 5 of homogeneous metrics on the limiting space. Okay, and that's 5 times of geometry was already classified given by Thurston. Okay, so however, it's still only thing here is still unclear. Finite time surgery are canonical, and we expect that there are only finite many models for finite time surgery. I already mentioned this before. Here I restated it. Okay, this is an open problem, and I put this in a bit vague way. Is that next definite way is say these results of Baumler should imply that after proper scaling convergence, and this step was not proved. But I do think this is a doable step. Okay, but it does require some further analysis, and it could be a good problem for PhD thesis, and or maybe more than one PhD thesis. Okay, So then you say, okay, I did so far is dimension 2 and dimension 3. What about high dimensions? Okay, the high dimensions, since first the Einstein metrics are not that rigid, okay, because in high dimension, curvature has more components than a Ricci curvature, okay. But nevertheless, this Ricci flow has found many applications. So, for example, in high dimension, if an initial metric satisfies stronger curvature condition, such that the positive curvature operator or isotropically positive curvature, then this curvature condition is preserved. This was done by a group of people. For example, you can, in a quarter pinching case, if we assume there's a non-standing problem in differential geometry, it's called if we are giving a space, if a curvature at every point is the maximum and the minimum, maximum over minimum is less than 4, called the quarter pinch problem. Namely, the minimum over maximum is bigger than 1/4. Okay, strictly bigger than 1/4. Then you ask whether this is what is this space? It turns out this is a standard field. Only space is standard field. And this theorem previously studied by many people since Klingenberg and so on, and various conditions, and using a generalized boundary conjecture only proof topologically is a sphere. But diffeomorphic sphere eventually was done by Brandl and Rick Schoen by using a Ricci flow. Okay? Also, it's for curvature operator, positive, that was done by Baumer and Wilkin by using a Ricci flow. And previously, again, was only known in lower dimensions and in dimension 4, and also only proof is homeomorphic by using a generalized boundary conjecture. So this shows the Ricci flow is powerful even in high dimensions. So actually, also isotropically positive curvature, this problem is still open. It's still not completely solved. Try to classify the space with isotropic positive curvature. Dimension 3 is trivial. We don't worry about that. And dimension 4, that was done by Richard Hamilton, and there's something completed by Chen Binglong and Zhu Xiping. Okay, so in the high dimensions, it was done, and some minor conditions by Brandl himself when the dimension bigger to 12, and my current student, who is only a second year graduate student, and he solved during his first year graduate study and generalized Simon Brandl's work to 9, 10, 11. So what's open now is a dimension between is 5, 6, 7, 8. Okay. So anyway, so there are still questions left. So what about the possible application of Ricci flow? And in high dimensions, if we do not impose the positivity conditions, okay, on the initial metrics. So on the previous page, we assume this is always some positivity conditions. Okay? So one possible application is in dimension 4, which I mentioned before in some other talks. So if one can construct such a flow in dimension 4, and one may be able to prove a following conjecture, which is called this conjecture is about the Beatty numbers and the signature closed spin for manifold. So don't worry about what spin for manifold. So for simply connected, is clear. So it's giving a closed for manifold. Suppose it's a spin. Spin means anyway. Spin means it's mild conditions. Okay, so it's a secondary class equals vanishes or structural group can be lifted to a spin 4. Okay, whatever. So anyway, it's simply connected, and then you want to prove second Beatty number is always bigger to 11/8 times the absolute value of a signature. Okay, the sigma m is a signature, namely it's because it's a 4-manifold. We know SO4, the 4-dimensional orthogonal group of the Lie algebra, it can be essentially split into 2 copies of SO3. So in dimension 4, there's a so-called self-duality conditions. Okay, so that on the H2, you have a B plus and a B minus. Signature is simply a B plus minus B minus. So it's okay. So anyway, so you have this inequality here, and this there have been many works. For example, use Simon's work, Simon Donaldson's work, and this polynomial invariance, Donaldson invariance, and all its generalization, and it was proved is this B2 bigger equal to 10/8, but not 11/8, and this one difference makes a big difference. Okay, so what is the implication of this? A formation of this inequality will yield a classification of closed simply form manifold of, or I should say spin form manifold, smooth spin form manifold up to homomorphisms. Namely, you can completely understood for smooth form manifold, spin form manifold simply connected, its second intersection form is completely determined. Then by Michael Friedman's result, you can know the diffeomorphism type. Okay, so rich flow may give this may have this application. Of course, then you need to do as we did for dimension 3. You need to know how this finite time singularity get, at least topologically, and what a limiting metric might be. Okay, so a few years ago, I don't think Baumler developed this proposed 3 preprints, developed the regularity theory on the rich flow in high dimensions. I guess this paper not completely published yet. It takes time. It's 300 pages more than. So they shed light on the construction of rich flow with surgery in dimension 4, such that its topology can be controlled. Okay, so this is one application, and for rich flow in dimension 4, we in the general, without assuming a priority, the curvature has positivities. So another example, another thing in dimension 3, I always curious. I have been, but this is a difficult question. So thinking about this, at least to me, and I was wondering about these things for many, many years, and I haven't found a good solution. So I pose as a question here. So in dimension 4, there are also other kind of elliptic equations. And this kind of equations were studied by many people. So this is called anti-self-dual metrics. So in dimension 4, you take a curvature. Okay, curvature is look at the curvature operator is a 6x6 matrix. Look at point, because it's from a wedge 2 of a tangent space to a wedge 2 of tangent space. It's symmetric tensor. Okay, so it's 6x6. This symmetric matrix, the curvature operator. Okay, and however, as I said, this is a structure group is SO4. So SO4 is the algebra is a 4x4 orthogonal matrix. So it's the algebra is a 4x4 schizometric matrix. It can be written as 2 copies of SO3, right? So then you have a so-called self-dual, anti-self-dual. You can do this decomposition of a 6x6 matrix on the curvature operator, become a 3 times 3 blocks, and 3 times 3 blocks, and off diagonal 2 things. Okay, and this diagonal 3 blocks, 3 by 3 block is essentially by a so-called Weyl tensor. Okay, so that you look at the plus part or minus 5 is actually they are identical, I mean, kind of equivalent, okay? Depends on how you orientate it. So you can have a W plus. This is a 3 plus 3. Metric, symmetric, and the chase 0. So it's 3 equations. So W plus equals 0. And if you plus scalar curvature to be constant, you get 4 equations. That's still a kind of elliptic type, okay? It's a determinate type of equations. So it's a simple observation is if your M is homotopic to a force field and admits anti-self-dual metric, namely W plus equal to 0, then you can prove it's a diffeomorphic force field. We know the 4-dimensional Poincare conjecture was proved by Michael Friedman in 1982, but whether or not S4 has an exotic differentiable structure is still unknown, so-called smooth 4-dimensional Poincare conjecture. And at least if there's an exotic metric on the S4, exotic differentiable structure on the S4, then this exotic structure does not admit anti-self-dual metrics. Okay? So there are many examples of anti-self-dual metrics. For example, Cliff-Tops proved if given any four manifold, you make a connect sum of CP2 enough sufficient many copies of S2, CP2, then you have a constant. You can have an anti-self-dual matrix. You have a metric with W plus equal to 0. So and also there's in British school there's a called a method of twist space construction. You can construct many examples of anti-self-dual matrix, but this method does not so far not useful to this question because in these things we cannot add the copies. We want to reverse the process. I want to decompose, cut off a bad part, and eventually get anti-self-dual matrix. So namely, we want to have something like a rich flow. It is to deforming or giving metric towards anti-self-dual matrix, possibly through finite many surgeries. Okay, and the method here so is whether or not you can find such a flow. Okay, this flow is not a rich flow, but I want to find a flow evolution process. Even though this evolution process may have a complicated analytical problem, at least in principle, if I have a strong analytical skill, I'm a Superman in the analytical skills, then this process will give me a solution. Okay? And this process is unknown. So another important case, I will quickly go through this because another important case is to study rich flow is called study Kähler manifold. This is also special kinds of manifolds, which include all the algebraic ones, all the manifolds defined as zeros or polynomials. Okay, so this manifold can be characterized as follows. So called again we can say the compact closed one. So I say a metric is a Kähler. The first is a metric is a Hermitian. Okay, so in general the metric is positive definite symmetric matrix. So here I want to make a constraint because underlying space has a complex structure. So I want this metric to be a Hermitian positive matrix valued functions. So this is one restriction. And that's not enough. Now another restriction is if I define this omega, which is a two-form, and it turns out this two-form is globally defined, even if Gi, J bar, this Hermitian positive matrix valued function it depends on the choice of coordinates, but this form is closed. So G being Kähler equivalent to d omega is 0. So omega is closed. And this condition means if we recall what we learned in the calculus, locally, any closed form or giving a one vector, if a curl of this vector is 0, we can write this vector as a derivative of differential of a function, locally at least. Okay, so this condition simply means this is a compressified version of that. Namely, the omega can be written as a Hessing, complex Hessing of a function. Okay, so locally, Kähler metric is given by one function. So what's the good thing about this Ricci flow is preserve this structure. Namely, if an initial metric is Kählerian, then so does the GT along the Ricci flow. So does the solution along the Ricci flow. So many years ago, actually, in my talk in the ICM 2002, actually we proposed starting this called we call it analytical minimum mode program. At the beginning, we just try to understand the finite time singularity formation. So this process is like what we did in dimension 3, imitated. Okay, so except this in this Kähler case, there are more cases. Because there are more examples and the structure becomes even more complicated, but still seem to be doable. So first, understand the finite time singularities and construct a solution with surgery. Okay, and second, show such a solution converges to a canonical Kähler metric on the limit. Okay, so and such a canonical metric include the Kähler inside metric, and many progress has been made. There are many papers on that since we formally proposed this program 20 years ago. We can verify this both things in the on a certain algebraic manifolds by using a certain results from algebraic geometry. Okay. Of course, eventually we don't want to use the knowledge from algebraic geometry because if we can do that purely analytically or differential geometrically, we can not only do it for algebraic manifold, we can also do general Kähler manifolds. Okay, so this actually second case is almost done. The main problem still is the first case. Okay, so to illustrate the beauty of a Ricci flow for Kähler manifolds, we just called a simple result. Okay, it's called the sharp local existence theorem. So in general, for general Ricci flow, the local existence theorem is you don't know how big the T is. There is a criterion due to Richard Hamilton, later on due to my former student Natasha Sesson. Namely, this if how to characterize the capital T when you can solve the maximum T, where you can solve the Ricci flow from 0 to capital T. The criterion is that the Ricci curve has to blow up, has to go to infinity. So namely, your space has to be curved, very, very, very curved. Okay, so however, in a Kähler case, there is a simple cohomological criterion, or can say it's topological criterion. So namely, this you can say the Kähler Ricci flow has a unique maximum solution, and the capital T is characterized by this cohomologic class. Okay, and this can be easily determined giving a space. Okay, so that's this. Of course, this is not difficult theorem, but I just want to use this to illustrate. In the Kähler Ricci flow, in the Kähler case, the Ricci flow behaves much better than the general case. So, particularly if it says if a function class is not positive, capital T, you must develop a finite time singularities. And the difficulty part, as I said, is understood finite time singularity. There has been many results and understandings. And for second part, about long time was first given by Song Jian by myself. And we only prove a kind of C0, I shouldn't say. On the metric level is, on the potential level is C0. So it's a weak convergence. Okay, and they more recently, actually, this year was finally improved by by Han and Prasadi, and to a smooth convergence. Okay, once. Of course, smooth convergence are outside some singular set. Okay, outside some sub-variety of codimension, complex codimension, at least one. Okay. So there are also other interesting examples I quickly go through. So rich flow does not solve every problem, and for example, there are other interesting geometric flows. And for example, I said the rich flow preserve Kählerian conditions, but if I giving a metric is only a Hermitian metric, it does not have this d omega equal to 0 condition. Then rich flow does not preserve that Hermitian structures. Okay, so more than 10 years ago, Jeff Scherz and I introduced a family of new curvature flow on the Hermitian metrics, trying to understand the complex manifolds. In fact, we do not have motivation. Our motivation was the following. In fact, even we knew a lot about algebraic geometry, a lot about the Kähler manifolds, for example, Calabi-Yau theorem, and so on. But we didn't know much. We did compared to Kähler case, we didn't know much about the complex manifold which do not admit the Kähler structures. Okay, and for example, simplex example, whether S6 has a complex structure, many people tried. So far, I'm not sure. Okay, so we developed an analytical theory for this curvature flow, analogous to this. There's some analytical theory like derivative estimate and so on. So like what Hamilton and Shi Wanqiong did many years ago. So there are two particular important cases of this flow. Namely, one depends on how you choose this nonlinear term, the Q term. So one is we use this particular Q. Okay, T is a torsion, because in a general Hermitian manifold, it's non-Kähler case. So you have a metric, you have a complex structure. Now you want to choose a connection, which which make a metric parallel, and which is torsion-free. That's a Navier-Civita connection. But if you want to make a complex, you preserve a complex structure, then this metric has to be Kähler. Okay. So in general, you have three things: the metric, complex structure, and the torsion. You cannot have three of them simultaneously without on a general complex manifold. So that's why we put the torsion here. Okay, torsion here. So usually when we study complex manifold, we want to use a connection called a Chen connection, which preserve a metric and preserve a complex structure, but it has torsion. It has torsion. Okay, so it preserves some closer things. So don't worry. So this is just special class of things. So first, this flow is a gradient flow, like in the Perman proved for Ricci flow, and it's also preserved generalized Kähler structure, which was first proposed by Hitchin and his his students. And but this generalized Kähler structure, so whether how to classify this kind of manifolds. They are not Kähler manifolds, but they are still very special class of complex manifold. So another thing I'm particularly interested is actually that was my motivation when Jeff Scherz came to be my postdoc at Princeton, and so I pursued him to study something. So there is say I said a pluriclosed flow. So there's for four manifolds. We may use a pluriclosed flow studies of class 7 surfaces. This class 7 surface was not Kähler surface. In the cordially classification, and this is another topic I was very interested, influenced by Fabrizio Catanisi. So when I was a student, so I was curious about class 7 surfaces are. That's actually still mysterious part of classification of complex surfaces. So this flow might provide something like that. Okay. So anyway, so another important case was studied by my former student Yuri Utinovsky. So he used a different expression of this torsion form. Okay. He proved that this flow preserves Griffith's positivity. Okay. So this might be solved. This is Griffith positivity. Maybe I skip it now. Time is up. So maybe I stop here because there's also a class of flow starting a symplectic manifold, and my time is up. So I stop here. Thank you.
Other questions? Okay, no questions. Let's thank our speaker again. So lunch break.
Colleagues, there are many places, canteens on campus you can find, or you can walk to mega, huge shopping mall across the street, Kabambai. Many different restaurants there. So we will return to another building. It's block 2, please, for session talks at 2 p.m.